Okay, so in this chapter we'll be looking at refrigeration and heat pump systems. Heat pumps are an alternate use of refrigeration. So first we want to review concepts from Thermo 1 from the previous course, starting with when we began studying this with the second law of thermodynamics. But we're also going to combine with this our understanding of two very basic heat engines, the Rankine cycle and the Brayton cycle. And the really nice thing is that the refrigeration cycles that are used most often are essentially reversed Rankine cycles or reversed Brayton cycles. And so we'll be taking a look at those in this chapter. Now, if you'll recall, a refrigerator is a device that operates in a cycle and requires power. Conversely, the heat engine was a device that operates in a cycle and produces power. A cycle meaning that the initial state is the same as the final state, and power being the net power of all the different places where work is done or required. And so refrigerators are going to require power, meaning that the work is going to be into the system. Now we have two choices of goals. One may be that my goal is to take heat out of something that's essentially already cool. That's what a refrigerator or an air conditioner does. If I'm air conditioning on a hot day, I'm taking heat out of my house that's cool and putting it into the outside that is significantly warmer. Similarly, my refrigerator takes heat out of that cold space where my food is and puts it into the room that is warmer. But I can also operate this thinking in terms of the heat output to something warm, and that would be a heat pump. And this can be used for heating and cooling homes, or it may be that I'm just huddling behind my refrigerator trying to get a little bit of extra warmth on a cold day. So, when I want to measure performance of cycles, sort of the generic definition says that how good a design is can be quantified by looking at the desired effect divided by the cost or energy input. Okay, and when we talked about engines, that the desired effect was power output, and the cost was our, fuel cost. This is going to be different. A refrigerator, my goal is to cool the cold food, so Q sub L. My cost is the power I have to put into it because I have to pay someone for that electricity. So QL over W net is going to be my coefficient of performance. Some places use beta for the notation for this, some just use COP. Either way, we need to indicate whether we're acting as a refrigerator or a heat pump, so we'll put a subscript R on either one of these. Now, I don't want to have to worry about signs, whether I'm remembering that heat in is positive and heat out is negative. QL, in fact, would be heat into the system, so that would be positive, but at a low temperature. W net is going to be the network input, so that's negative. So I need an absolute value in order to get a positive quantity here. Now the other thing I need to recall is that W net is the same as Q net, so the net work input will be equal to the net heat input. If I do simple balance on a simple little system like this with one heat input, one heat output at QL or at TH and TL, I can also rearrange this. Q net is going to be my QH minus my QL if I put absolute values on them, or I can rewrite it in this way. I can do a very similar thing if I'm thinking about a heat pump, where my goal now is the heat output to something that's already warmer than my low temperature. So QH, but the cost is still the same, W net. Again, the same sort of balances and putting in absolute values just to make sure that we don't ever get tripped up about signs. 1 minus the value of QL over QH, the reciprocal of that is going to be the coefficient of performance of the heat pump. Now, we typically want to compare actual to ideal cycles, and so to do that we consider the best possible cycle. And I've already alluded to we are going to be using reversed Rankine and reversed Brayton cycles as our models of how we will really build a refrigerator. But just like our Carnot cycle was our best possible engine, if I reverse it, that makes my best possible refrigerator. So for that best possible totally reversible heat engine or totally reversible refrigerator, I could relate these measures of performance to temperatures. So in the case of a refrigerator, I find that it's TL over TH minus TL. And for a heat pump, it's TH over TH minus TL. Now, think about this. This means that I'm going to always have something that is going to be greater than 1 in these cases, okay? Which is not really the same as what we had before, okay? So I've got my ways of measuring performance, and I've got a way of evaluating whether or not my answer is realistic or not by looking at the Carnot efficiency for a refrigerator or for a heat pump. So at this point I'm going to break the video and we'll come back and look at our first refrigeration cycle.